time on one half or the other. Maybe work out exactly where halfway through your test will be, and once you hit that point, make sure you switch from either algebra to calculus or calculus to algebra, depending on which one you want to try and do first. Okay, so the first question is going to be presented by Daniel. So Daniel, do you want to see there? Maybe not. Do you want to present the first question?
Okay.
Or do you have any other advice you want to remind them about?
I think I accidentally chopped off most of your advice. The
Oh,
only
right,
bit they
okay.
saw was the bit where you told them to chop it in half.
Okay.
So
I
can
think
you
you're
repeat the
invisible.
advice before that? I mean, I'm not visible, am I? Cool.
No.
Hello. Yeah, the bit that...
Yes.
Can you do that bit again?
So the
And
make
all
sure.
the bits before it?
I don't know what I said now. Well, I mean, you know, you've done test 1, so test 2 is not going to be a surprise to you. But yeah, make sure you've been looking at the course syllabus. Make sure you know what topics are being covered in this test. We're going to go and try and go over most of them, but we won't promise to cover all the topics in this live stream. Just as many as we can before we get tired.
Yeah, but we have stimulants, so we should be alright for a while. Cool. So this one is hopefully clear to you. Determine the conditions on the B's, which are needed to ensure that that B belongs to the span of the other vectors. And I might just define for you the span, because maybe that's familiar or unfamiliar, or was familiar and now you've forgotten it. So the vector B is in the span of these vectors. When B can be expressed as a linear combination of those factors. That means when there exists lambda 1, lambda 2, lambda 3 elements of the real numbers such that lambda 1 Okay, so what does all that mean? You would have seen this, perhaps the most familiar way you would have seen this in lectures is for the span of two vectors, where you take this vector and you take this vector and you bust the span on them, which gives you all the vectors which can be created using a bit of this vector and a bit of this vector. But now we're doing it with three vectors, so you've got, the question is usually, can you construct a B of this shape given some amount of this vector plus some amount of this vector plus some amount of this vector? Now this question's a bit different. It's asking you instead for all the possible B's that can be constructed in this way, or some condition on the coefficients B1, B2, B3, B4, which exist in the span of these vectors. So it's a bit different. But the method is the same. I mean, this is essentially a system of linear equations. And there's only one way to solve a system of linear equations. You throw it into a matrix and you row reduce. So that's exactly what we'll do. You may like to ponder to yourself, is he going to go to reduced row echelon form, or will he stop at row echelon form? Well, we just want to know if they exist, so you can hopefully answer that for yourselves. And if not, I'll just take a minute to get to the answer. Good. We have this lovely augmented matrix. There's only one thing to do, get it into row echelon form. So I'll do that with a, well, I'm going to do 3 row operations at once here. You may like to do only 1 row operation at once. I'm going to do 3. So Josh, is that visible? This
Yep, still visible.
Cool, thank you. Have I got much space?
Yeah, about a half a matrix more.
Nice, that's what I need.
In space below or space to the side?
It's to the side.
Yeah, about half a matrix.
Nice.
Nice now. Let's see.
Good, it's looking a little bit more like a row echelon form, so -5. I just need to kill off these terms, and of course I can do that quite easily. Row. And minus plus b2, and I've got negative b1, and I take away another 2b1, that's 3b1. And I've got negative 4b1, I add 2b1, I get minus 2b1. Good. And now my matrix is in what I hope is row echelon form. Remember, this matrix has solutions exactly when, look, this is a leading term, this is a leading term. This matrix will have solutions exactly when this is a non-leading row and this is a non-leading row. And those are my conditions. I need to choose my b's that make this not leading, i.e. I make this 0. And I need to choose my b's which make this not leading, i.e. 0. So i.e. these are my 2 conditions on the b's. Now, that's all well and good. You could probably do that, but how might you check your answer? And to check your answer, you need a little bit of an understanding of geometry, which I'd like to kind of deviate and give you for a moment. Remember, this is the span of vectors. So you take all these 3 vectors and you just create, the b is supposed to represent anything that could be created using these 3 vectors. And of course, what's some easy things that could be created using those 3 vectors? Well, that. You should be able to create that using these 3 vectors. And so to check our answer, we could sub that into here to make sure that, well, we can create this vector, which if you understand geometrically what the span is, you can do. So let's just do a quickie check. A quick check. Check is that 1, 2, 4, 1. Satisfies these conditions well. Be 3, 4 minus twice the second component. Oh, sorry, minus the second component minus twice the first component is equal to 0. And what's the other one? Fourth component, 1 plus the second component minus 3 times the first component is also equal to 0. So I'm pretty confident at this stage that my conditions do in fact represent the conditions on the B's to be in the span, because I at least checked one thing to make sure that I didn't make any mistakes and get my pluses and minuses mixed up. Josh.
Right. So yes, this is a long question. It does require a lot of explanation.
You'll be behind the thing.
Yes,
you stand there.
But yeah, I think it is important to realise. Actually, that reminds me. Someone did ask a question just in the chat then about whether chapter 2 material was in the test. This is actually chapter 4 material about systems of linear equations, but we are using vectors and spans to get a system of linear equations to solve. So yeah, I think it's important to have this first step where you explain that you know where the problem's coming from. This is about solving system of linear equations, and you want to show where these equations are coming from. I know a lot of students want to skip straight to this step, but I think we should respect what problem we're trying to solve.
Yeah, I like the question much better if you understand what it's actually asking you in a geometric sense. And if you do understand it, then you kind of can check your answers to kind of just sanity check, what do these conditions mean? The conditions mean that these conditions are just conditions you can apply on these vectors, or any vector, to see if it's in the span.
Right. Yeah, so this is nice. I guess the question for you, what would you do if it didn't come up 0?
I'd start again.
Okay.
Look, if it didn't come up 0, then I've made some mistake in here, and I'm not going to spend 5 minutes sifting through all this junk to find where my mistake is. I just throw it all away and start again.
Yeah. I think personally what I would do in that situation is I've made a mistake. I'm not in a good mood to make a mistake immediately again. I might move on to the next question and come back to this one.
Yeah, that's good advice.
At the very least, I know what I've demonstrated. I know the technique, so I should be getting marks for demonstrating a nice technique and nice explanation.
Yeah. Okay.
But it would.
Duck. I can still be in the screen like this.
Yes. At this stage, I mean, if you do this and go, "Oops, I've made a mistake," just come back to it later. When you make a mistake, it's very hard to start spotting what's going wrong. Someone was asking about where you choose to put these. I don't think that's too important. I mean,
you need to put them somewhere.
Somewhere, yes. Wherever there's space is probably the correct answer. We actually probably do spend too much time thinking about typesetting than you realise. But no, here, I think this is good. He could have put a row operation up here, but this looks nice. It's easy to read, and that's the important thing. It's easy for people to understand what you're doing. This is a perfect solution. There's no way you could really make it shorter without losing comprehensibility. So I think that's good. Probably should move on to the next question. So if you click it over.
Yep.
Alright. Cloth. So hopefully it's appeared by now. So I'm going to do this question. It's actually a fairly short question. So we want to take sine, the fifth pair of sine, and express that in terms of sines of multiple angles. So it says there in terms of sine of 5 theta, sine of 3 theta. Now this feels more like a calculus problem than an algebra problem, but we can use the magic of complex numbers to make this happen quite nicely. I really like this problem, especially from how I can use it in calculus to do a lot of things. Okay. Right, so we're going to use this provided identity, and what does it say? Well, it would tell us that the fifth power of sine theta is really just the same as e to the I theta minus e to the minus I theta over 2I to the fifth power. Now, to make my life a little bit easier, I'm going to pull out the 2I to the fifth power. So this becomes 1 over 2I to the fifth power, and then e to the I theta minus e to the minus I theta to the 5. Alright, let's simplify this first. Well, 2 to the 5 is 32. That's just one I've seen so many times I now remember. And I to the power of 5. So I to the power of 5 is 2 minus 1s and an I, so it's just actually the same as I. And here we'll have to use the binomial theorem. So this is going to give us, and maybe I've forgotten the numbers. I need Pascal's triangle just very quickly to help me out. Oops. Right, so this is the row I need, 1, 5, 10, 10, 5, 1. Alright, so I'm going to get the fifth power of this. Now, the fifth power of this is just going to be e to the I 5 theta. And then I'm going to get, well, there's a minus sign here, so I'm going to get minus 5 e to the I 4 theta e to the minus I theta, which is the same as e to the I 3 theta, plus 10 e, and well, at this stage I'm going to just simplify this beforehand, so this will just be e to the I 3 theta. Here I'm going to get 3 of these and 2 of these, that's a 3 minus 2 is just an e to the I theta. Figure out pre-simplified. Minus 10 e to the minus I theta. So that's really a 2 theta minus a 3 theta, if you get that. And 2 more. So I think I'm getting close to the edge, so I'm going to put them down here just in case.
You got space, Josh.
Okay. Let's see. Minus plus minus plus e to the I 3 theta. I should double check that, but the pattern tells me that should be right. A minus e to the I theta.
5 theta.
5 theta, yes. Minus 5 theta. Oh, I've made a mistake, haven't I? This is what I get for trying to do it too fast. So yeah, there should be a minus 3 and a minus 5. If you look at how the powers are combining, they'll go 5, 3, 1, minus 1, minus 3, minus 5. Now, what I'm going to do is actually use this formula now in reverse and collect everything so they look like signs. So this one and this one will combine together, and I will also borrow a 2i from here. So let's see how I'll write this. So I'm going to borrow 2i from here. So this is 1/16 of, well, this one and this one together, e to the I 5 theta minus e to the minus I 5 theta over 2i. We have, got to be careful here, minus 5 times e to the I 3 theta. I have forgotten a 5 here. So yeah, there's a 5 missing there, should be very careful. So to make that a plus 5, I need a minus e to minus 3i theta, 2i. And the last term is these 10s, a plus 10 e to the I theta minus e to the minus I theta over 2i. Right. So this is nice because if you look at this, this is really just a sine, but with a 5 theta instead of a theta. So by looking at what I have, this is the sine of 5 theta. Here I was very careful to make sure I pulled out the minus 5 to begin with, because this is just actually sine of 3 theta. Okay, minus 5 sine of 3 theta. And this last one is plus 10 times sine, just theta. And that's really all they want. So you now have this somewhat complicated sine in terms of just a nice linear combination of these simpler sines.
Cool. And I might mention one practical reason why you might actually want to do this is to integrate sine 5 theta. So if you did get asked to integrate this thing, then you could rewrite it as a sum of sine of multiples of theta instead of power, and then you could and then that's rather easy to integrate. So there's a practical reason why you might actually want to do this. Aside from that, cool solution. Personally, I would have written it out longer,
right?
Especially in an exam situation. I don't want to be, as strange as it sounds, I don't want to be clever in an exam. No. I want to be mechanical in an exam and just churn it out. Not clever. I'd rather be mechanical.
Yeah, because one thing is you can see I did make several mistakes on the way, and if I hadn't, well, because I have done these problems before, I did pick up on these mistakes. I was expecting to have a 5 for this. So
yeah, you already knew what the answer was. That's not fair.
Well, I didn't know, but I knew it was going to be in terms of these, and if I wasn't getting that, I knew quite quickly where my mistake was going to be. So yes.
Cool.
Right.
I'm up. Where's the
they're all over here, sorry.
Oh, they're here? Cool, thank you. Hey Josh, I was thinking next time we could use like a transparent, could we do that transparently instead of having it white? Because then when I stand over here, you still see me with writing on my head.
I was trying to find that option right before we started.
Ah, okay, yeah. Because I'm watching you on the screen and I'm thinking, man, it'd be really good if that was transparent. We'll see what we can do before the final exam revision. Okay. Find complex square roots. Okay. Find complex square roots. Now this is the one time where you don't want to go to polar form because you can't really convert this number into its polar form representation. So instead, you can't go polar form, you have to go Cartesian form. Let x plus y be equal to the square root of this thing. Good, and now we just need to tease this apart, figure out what the x and the y could be. Well, the one thing we know about the square root is that when you square it, you should get negative 24 plus minus 70i. So we just square both sides. And this is something I could expand. Well, maybe I'll expand it down here. X squared minus. So just expand this out. And this is nice because it has a real component and an imaginary component. And it's supposed to be equal to this, which also has a real component and an imaginary component. So the real components must be equal and the imaginary components must be equal. And to make this very clear what's going on, we say we can equate the real and imaginary parts, much the same as you would equate a modulus in an argument. Equating the real parts gives us, And equating the imaginary parts gives us that 2xy is equal to negative 70. Notice the imaginary part does not include the I. The imaginary part is the coefficient of I. I can neaten this up some. That's going to give me x. Well, at least I can do it this way. X is going to be negative 35 over y. And I could sub that into here. It's two equations, two unknowns. This should work out, right? This gives me negative 35 over y squared minus y squared is equal to negative 24, which is a quadratic. This negative 35 is going to cause me some heartache, but I can deal. This becomes y squared minus 20, y squared squared. So that's y to the 4, but I'm going to write it as y squared squared. And minus 35 squared. 35 squared is 7 times 5. So maybe I'll write it as 7 times 5. Maybe I'll write it as 5 squared times 30. So it's 35 7 times 5, but I'll write this one as 5 squared times 7 squared. Suggestively as 5 squared times 7 squared. And that's supposed to be equal to 0. And 7 squared is 49, 5 squared is 25. So this is y squared minus 49, y squared plus 25. And there's only one way to deal with this. Y remember, is x and y are both real by the definition of Cartesian form of a complex number. So I can't have this as a solution. Y squared must be equal to 49. So y must be plus or minus 7. And if y is positive 7, then x must be 5. And if y is negative 7, then x must be... Did I say that right? If y is positive 7, x is negative 5. And if y is the negative 7, then x has to be positive 5. There we go, course equation 2. That's the worst plus. Plus or minus. Yeah. Good. And a simple thing to do would be to plug that back into... It would be to square this and see that you got that, which you will. So, there's my answer. Josh.
Yep, it's a good solution. And fairly quick too. Yeah, do...
Just stand over here.
Actually, no. I set it to 50% opacity.
Oh, nice.
They
All right.
Probably see me at least 50%, I think. Yeah, so I just played with it. So sorry for the flickering you would have seen when I was trying to put that setting on.
Cool.
Let's see. Oh yeah, so this is very important that there is a difference in sign between these two. Because if I only had... What information? So if I only knew that this was, say, plus and minus 7, well, I would naturally think there could be 4 options for this, but we know there can't be 4 options. We know that there are only ever 2 square roots of a complex number, and we even know sort of where they're situated in the complex plane. They're always plus and minus of each other. So yeah, once you find one of them, really the other one's easy to find. So yeah, you need to solve... Well, you do need to solve both of these equations, but it's very easy to forget this one when you're working for your solution.
I suppose it's less clear when if you just sub it back into this one which ones have the matching pluses and minuses.
Yeah, this one doesn't notice plus and minus signs on those, so it won't be able to pick it up. This one is the one which is taking care of the
This
sign.
one's a function, so it'll sort you out.
Yeah. Okay.
I'm up again.
Yes, you are. That's right. So
Cool. So I can stand over here and people can still see me. Awesome.
Yes.
What have I got? Complex roots and factorizing.
This test is no calculators, is that correct?
Yeah, no calculators. That's more of a statement of intent, by the way. If you're told no calculators, that means the test has been deliberately designed for you not to need a calculator or references and stuff like that. There's no table of integrals because we want you to not use one, and we've designed the questions with that in mind. So it's a statement of intent. Don't feel naked and weird because you have no calculator. You should be able to do it just fine without it. And as you see, even with the 35 squared, it's actually not so bad without a calculator. You just have to figure out what to do with the 35 squared. Find complex roots. So solve. I'll just write it as solve z to the 5 It's all wet still. Okay, now this is the one where you need polar form because it's got big power of z, and for all other powers of z other than finding square roots, you probably want to be using polar form. So I'm going to just let z, and I'll choose its polar form, e to the I theta, be a solution. So what does that mean? Well, it means that when I take z to the power 5, I should get 32. And what is 32? Well, this one's in polar form. That's just going to be r to the 5 e to the 5 theta I. And this one, 32 in polar form, is 2 to the 5 e to the 2 pi ki, where k is an integer. Notice I need all possible polar forms of this number. Not just its principal argument, but all possible polar forms. And of course, just like in the other question, we've got a complex number written in two different ways. In the other question, we had the complex number written in a Cartesian form so we could equate its real and imaginary part. Now we've got it in polar form so we can equate its modulus and argument. And we state this by just writing equate the modulus and the argument. So r has to be equal to 2, and notice with the argument I'm equating, but it's the 5 theta, not 5 theta I, it's the bit without the I. So 5 theta is 2 pi k, where k is just some integer, we don't quite know what yet, and it could be anything, could be everything, it's everything, it could be all possible integers, and theta is therefore equal to that, for all, and that's true for all possible integers. It's more useful though for us to write it as only the principal arguments, and so we can extract so of all these possible thetas, which one's a principal? Well, let's just choose some values of k and theta. Minus 2. Choose small values of k. Any 5 values of k will do, but you'll have to do some winding potentially, and it's just easier if you straight up choose the small ones. and by small I mean centered around 0. So when k is -2, that's minus 4. Behold my principal arguments. I've got 5 of them, and I was expecting 5 because this is a degree 5 polynomial, so I know I must get 5. And hence So I'm just combining these two together, the plus or minus 4. So this one and this one, I'll just write that as e to the 2e to the plus or minus 4 pi on 5i, 2e to the plus or minus 2 5 pi on 2 pi on 5i, and this one just sitting out there by itself, 2. And of course, you shouldn't be surprised that these occur in complex conjugate pairs because it's a polynomial with real coefficients. So that's always going to happen for you. The next part of the question asks you to write this as a polynomial, so that's part I. Part 2 asks you to write it as a polynomial in real, linear, and irreducible quadratic factors. And the first step to this is always, first of all, writing it out as linear complex factors and putting the complex conjugate roots in as factors next to each other. So z to the 5 minus 32 is equal to, well, if these are the roots of this polynomial, then the polynomial has the following factorization. Oh. I'm going to run over myself over here. So here it is written as written in complex linear factors, and the idea is that these two combine in a very nice way. These two actually combine into a real quadratic polynomial, and that quadratic polynomial is z squared minus twice the real component of this, which gives you 4 cos 4 pi on 5 z plus the modulus squared, which is 4. And similarly, these two combine to give you a nice quadratic. And this one stays as a linear factor. Cool. And I wouldn't go into any more detail than this. If you do happen to know what the cos of 2 pi on 5 is, then that's nice. I'm very proud of you, but just leave it.
Right. So do you think this step from here to here was, I mean, because there is a little bit of detail involved in just.
Yeah. Should we? Do you want to flesh that out?
Yeah, I think we should, because I don't.
You thought?
Yeah, I think it won't quite be so clear.
Why don't we get rid of this and?
Yeah. So I think this is one of the steps where I would be a bit more explicit. So let's okay. So let's just take these first two and just convince ourselves that this is actually true. So having z minus 2 e to the I 4 pi on 5, and z minus 2 e to the minus I 4 pi on 5. Now, this is just a product of two linear factors, and we're probably fairly comfortable about expanding these sort of things, so let's just do that. So we get a, well, this is nice, z squared, but we're going to have, in terms of the coefficients of z, let's see how I want to write this. I always have minus signs, so I'm going to write it as, maybe I'll do it slowly. So it's going to be this one times this, so minus 2 e to the I 4 pi on 5, z minus 2 e to the minus I 4 pi on 5, z, and then the product of these two, well, the nice thing here is that this is just a, well, these e's will just cancel each other out because they're both complex numbers of modulus 1 with the opposite principal argument. So this times this is really just 1. So it'll be plus 4. If I want to be very explicit, it will be e to the I 4 pi on 5, e to the minus I 4 pi on 5. I don't need any brackets. And these two do just cancel out to give me a 1. Alright, so that's nice. Let's just collect these middle terms up to give us z squared minus 2 with an e to the I 4 pi on 5. Very careful with the sign. This is now a plus e to the I, sorry, plus the minus 4 pi on 5. So the minus sign there. Z and that plus 4. And this one you should recognize it is just a number plus its complex conjugate. So when you have a number plus its complex conjugate, you will just get twice the real part. So if I want to be even more explicit, I can use the RE to the I theta expansion here, but I think at this stage I want to look at this and think this is twice the real part of this. So depending on how you're thinking about it, this will be minus 2 times 2 cosine of 4 pi over 5. Because I'm getting twice the real part of this. And the real part of this is quite easy, it's just the cosine. Z plus 4. So even now I'm skipping a few steps, but I think it's a little bit more explicit. If you didn't quite follow how this was done, this is the same answer. So these 2's combined to give you the 4, and you have the cosine 4 pi. Any comments?
No, that's all correct.
You do need to be careful here. It's very easy to forget about the factor of 2 here, because I did, again, the more I do in my head, the more probably not everything makes it out of my head onto the paper.
Yeah.
So.
I would recommend this is something you practice doing this, because when you get asked a question like this, you need to do this a lot. You need to do it here. I mean, if you've got a degree 8 polynomial, you'll need to do it another 2 times.
Yeah.
And you won't have time to do this 4 times over.
Yeah.
So I do really recommend you practice something like that and keep it in your pocket, because it's a nifty optimization. Anyway, cool.
So this is a good backup in case that optimization fails.
Yeah. Ideally, you do this before your exam. But anyway, it's going to work either way. Josh, you up.
All right. So you have to hide the other one.
Are you skipping that one?
Oh no! You'll have to when you make the next one visible, because it's opaque. You'll get the
I see. Right. So that one goes away, and that one appears. It's not opaque. Josh, I don't know what I'm doing.
Oh, right. Let me.
I know it. Oh wait.
Just. Oh, sorry. Yeah. So if you go down to the menu at the bottom,
yeah,
where the eyes are, just click on the.
Yeah.
So hide that one.
Hide it.
And show the next one. Next one up.
That one.
That should. Is that mine?
No, this one's yours. I've already done that bit, but it's not opaque.
Oh. Oh, that should be fine.
Do you want you make it opaque, and I'll clean the board.
Thanks.
Because I like the opaque thing. That's working well.
Hey, the filter's gone. Color key. Okay.
think you can copy the filters and just paste them.
Yeah. Alright, well, interesting. I'll just do that every time.
Yeah, we'll figure out how to do it the pro way next time.
Do it correctly. Yes. Right, so we have another system of linear equations to look at.
Cool. I might grab some tea while you shoot through that
yeah,
one.
This one probably will take a while. See where we are. So we have a system of linear equations, and it asks us to find the general solution. So we want to find all possible solutions, which means we're going to have a parameterized solution. And we definitely will need a parameter in this one because there are 3 equations and 4 unknowns. So even if you were to have all independent equations, you're still going to have 1 unknown left over in the end. Okay, so they were nice to us. This is already written out as a system of linear equations. Should be some commas, but never mind. And our technique for solving these is to use the augmented matrix approach. So we're going to put it in an augmented matrix and we're going to row reduce. Now, unlike the question Daniel had at the very start of the live stream, I probably want to reduce all the way down to reduced row echelon form. It's not necessary as long as you get down to row echelon form, but I find reduced row echelon form can be helpful in that back substitution step. Alright, so first things first, as an augmented matrix, better. So as an augmented matrix, the system of linear equations is, and here's where you have to be very careful. You want to make sure you do get the right coefficients. If you don't get the right coefficients, you're not solving the right problem. And there's a high chance that it won't actually have a very nice solution. Alright, so the first thing I should do here is actually look at the question again and make sure I'm solving the right problem. So according to this, the coefficients are 1, 3, minus 2, and I can see I have, in my haste, made an error. 4, 2, yes. Minus 2, 4, 5, minus 9, 0, yes. Minus 1, 1, 4, minus 6, and 6. So let me just double check all the placement of the minus signs. Minus, 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 yes. So this is now the correct problem to solve. So let's do some row operations and solve it. Now, I actually do like to go and circle the leading entries just so I know what I'm doing, what my goal is for each of these. So I have these 3 leading entries, and leading entries are, well, like Highlanders, they can only be 1 in each column. That reference won't age me very well. But yeah, this 2, I don't want this 2, I'm going to get rid of it. So I'm going to use this 1 to get rid of it. So my row operation to begin with is to take row 2 and add twice row 1. Right, so first row does not change. This is, right, so the whole point for doing this is I'm going to take this and add 2 of those to get 0. That's what my whole goal. Now this one, I doubled it to get a 6, added on to get a 2. I double this to get a minus 4, added on to get a 1. Let's double check that, yep. Double this to 8, added on to get a minus 1, and I'm going to add on 2 of those, which is 4. Alright, now I'm going to do another row operation simultaneously. which is to take row 3 and just add on row 1. So this was kind of very nicely designed to have minus signs in it. So again, minus 1 plus 1 is 0. This was the whole point. This plus this is 4. 4 plus minus 2 is 2. Minus 6 plus 4 is minus 2. And 6 plus 2 is 8. Now I can actually see what's already happening with this last row, but let's do one more operation to really make that clear. So my next goal is, this is fine sitting by itself. It's these two that are in conflict. So let's use that 2 to get rid of that 4. Take row 3 is row 3 minus twice row 2. I haven't changed the first 2 rows. So these zeros don't do anything. 2 minus 4 is 0, that was why I did it. 2 minus 2, because that's doubling that, is 0. This becomes a minus 2, so minus 2 minus minus 2. Well, I can see that these cancel out. And finally, 8 minus 8 is 0. Alright, so that's row echelon form. And at this stage, I can actually begin back substituting if I want to. But I think it probably will be better if I go all the way to reduced row echelon form.
I'd go reduced row echelon.
Yeah. So, right. First thing I'm going to do then is make this into a 1. Unfortunately that will give me halves here. It's not so pleasant, but they're not too bad. So I would probably have more space on paper. So usually I would be just continuing on with row 2 is going to be a half of row 2. Right. And how much space do I have? A bit more? Should I?
Yeah, you can do another matrix there.
All right. Okay, so
Don't go too.
don't go too far down. Yeah, very small. Okay, I'll keep it very short. So now I want to get rid of this 3, and well, that's easy because that's the nice thing about making this 1 is I'm just going to subtract 3 of this row. So row 1 will be row 1 minus 3 times row 2. Alright, so I hope this one's easy because it's 3 minus 3.
You can go bigger than that.
Oh, sorry. Just want to be careful.
Yeah.
Alright, so 3 minus 3, easy, 0. Alright, this one I need to be careful. I'm going to get rid of this minus 3 halves. So it is minus 4 halves. Minus 3 halves is minus 7 halves. So I get minus 7 halves. Feel free to do this on scrap paper if you want to make sure you're getting it right. I'm probably only getting this right because I did it before. This one will be 4 plus 3 halves. So 8 halves and 3 halves is 11 halves. So 11 over 2. And ooh, one more. This one's actually fairly nice. Yeah, this one's fairly nice, I think. Is it just this minus 6? So 2 minus 6 is minus 4. I think that's right. 0, 1, half, minus a half, 2, and there's no information. Right, from the last row. And again, just don't need to circle these, but I like circling them because I can see what's going on. Okay, now the beauty of the reduced row echelon form is that when it comes to back substitution, it's a lot easier. I've already taken care of the the details I would otherwise have to deal with here. And I think I can do it much easier in this nice, clean, augmented matrix form. All right, so that's not the end of the question. We do need to actually solve. And so there are going to be some parameters in our solution, and they're going to correspond to these non-leading columns. So I'm going to set these as parameters and then solve for the other two. Let's set, say, what was the original notation? X. So let's set x3 equals lambda, say 1, and x4 equals lambda 2.
A little high.
A little high?
Maybe get rid of the we get.
Okay. Can you see this?
And do the lambda 2 a little bit lower.
Alright. X. That's
Yeah.
Right. Well, the nice thing about this is I can solve for both of these. Well, I don't even need to know anything about x2 because it doesn't appear in this. So I get x1 is equal to, according to this, well, it's -4 plus 7 over 2. This is x3, which I called lambda 1. Maybe this is a little bit quick. Minus 11 over 2 lambda 2. x2, according to this, it's going to be 2. I'm going to shift these terms to the other side, so it's a minus 1/2 lambda 1 plus 1/2 lambda 2. And I would be happy with that as a solution. What do you?
Yeah, I'm happy just up there as a solution.
Yeah.
Cool. Did you mention how you chose, or why you chose x3 and x4 to be lambda, to be kind of free?
Yeah. Well.
Parameters?
So, I mean, if you were just ignoring trying to solve for parameters now, this really can be turned into an equation just telling me what x2 is equal to what x3 is equal. But when you get those, you're going to have these x3 and x4 just floating around as things, unknowns that you sort of have control over. And I want to treat them like parameters, so I should probably give them a name which is like a parameter. You don't have to choose these names. I mean, I chose lambda 1. I sort of chose them in the order which I saw them. I think it's nice to have lambda 1 and lambda 2, but they're really up to you.
Yeah. I just want to point out that these non-leading columns here, when you've got in reduced row echelon form, especially reduced row echelon form, what you've done is taken the system of linear equations and really just simplified it as much as it can possibly be simplified. But even still, there's x2 depends on x3 and x4, and x1 depends on x3 and x4. So what's really happening here is x3 and x4 are free to do whatever they like, and x1 and x2 get determined from them. And we kind of traditionally write variables that can do whatever they like. They're unrestricted, and we give them these names, and we call them parameters. So whenever you have non-leading columns like this, they're your free variables. This column here for x3 is free, and this one is free, and so we let them be free, and we denote it like that, and then we just figure out what the x1 and x2 have to be in those terms.
Yeah.
Cool. Was that the end of the question? I suppose it is.
I think it is. Yeah, that's a general solution.
Nice.
Yeah, there's no need to go to vector form or anything like that. Just this is a general solution.
Cool. Now, did you apply the filter to the next slide?
I don't think I've done that yet.
Cool. Can I try that? Because I've copied the filter, and now I want to paste the filter and see what happens. So I'll go here and I'll paste filter, and then, haha! Yeah. I'm just going to paste the filters on the rest of them.
Alright, cool. Thanks.
we're good. Thank you. Okay. Use the definition of the derivative to show that the derivative of some function is some other function. Okay, then. I mean, you should all know how to differentiate this function. The question is really, do you know how to apply the formal definition of derivative? Equals lim. Behold the formal definition of limit. And then we just plug in what f is, we turn the handle, and hopefully we get what we're supposed to get. So this is lim. So what happens here? I can expand this one out. It becomes -2. Okay. And I get some lovely cancelling. That cancels with that. That cancels with that. And everything else has a h in it. So I can write this as lim as -4x minus 2h plus h. Well, that's just going to give me -h. No, that's -2h squared. So that is -2 plus 1 times h all over h. So the -4xh, that one, and then I can just set h to be equal to 0, and I get -4x plus 1, which is exactly what I was hoping to get. Cool, Josh.
Yep.
Got an easy one.
Yeah. So this is a fairly quick question. It's really kind of checking. Do you remember the formal definition? I have seen students do something funny in the past, in that they came to this limit here, which is, well, if you look carefully, it's a limit of something going to 0 over something going to 0, and our mind is kind of tuned to see L'Hopital's rule. But there is a big issue with using L'Hopital's rule here, is that you're using a derivative. So that doesn't really make sense if you're trying to do it formally. You're sort of stealing information from the future in some sense. I'm not sure how I'd say it. So you really should be doing this. You should be calculating the limit explicitly. The question is quite nice. You can explicitly get this limit. You don't need to go to anything fancy tools to get it.
Yeah, I'd say it's more like using a tractor when you could use a shovel.
Right, yes.
Yeah, or a spade. There's not a lot to this question. There's certainly nothing of that kind of advanced technology.
Yes.
Cool. Yeah, look, I'd be impressed not with the answer. I mean, you even get given what the answer is. If you didn't know it already, how to differentiate this function to get that, there's no real marks associated to knowing what the answer is. It's really, do you know this definition, and are you able to apply it sensibly?
Yep.
So I'd say this is what, a 1 mark question?
Yeah, I feel it.
I don't
this 1 mark. It's a very quick sort of.
Yeah, and really, do you know the definition, and you don't do anything stupid on the way through to the answer.
switch the question over.
Yeah.
So the next question is about the mean value theorem. So you actually have to state what the mean value theorem is, and you do need to make sure you get all the conditions correct. There are a lot of parts to the mean value theorem. You want to make sure you do get them correct. So the mean value theorem says that, oops, terrible. So that if f is a continuous function over an interval, in this case a closed interval, so it does need to be closed interval. And it has to be differentiable over the open interval. Now, do say open interval because you don't need the endpoints. If you're putting the endpoints in here, you're sort of putting another tight restriction on your function. You don't actually need the endpoints to be differentiable. So then what does the mean value theorem promise? Well, it says that there is a C in the open interval AB, so it doesn't need to be the endpoints. There is a C such that, well, the derivative at that point C is equal to the average slope, mean slope. So this is the mean and mean value theorem. It's the average slope here. So you can see it's f of b minus f of a over b minus a. So yeah, there are a lot of parts to this. If I was looking at your work, I do want to see, well, I want to see this continuous over this interval, differentiable over this interval. The C has to be in here and this statement. So there's actually a lot of parts to this that you need to get right. Now, we want to actually find a point which satisfies that theorem for a particular function here. So it's a nice cubic function. Right. So we're going to need to plug in the endpoints. So we'll have to work out what these numbers are. Now this does take space, so I will rub this out. Any comments? No? So yeah.
Are you going to draw it, Josh?
I might give it a try. I mean, to be honest, I didn't have quite as much time to do this, so this one's on the fly.
Okay.
So I might.
Can I draw it?
If you like. So it's a cubic. I probably, if I wanted to draw it properly, have to work out where the turning points are.
Yeah, cool.
The mean value theorem.
It'd be nice to be able to state it somewhat.
Okay.
Because I think the picture for this really says about as much as the theorem does.
Right. Okay.
So maybe we'll just draw it down here.
Okay.
So, and then you can have space to say what's going on. So let's have the kind of.
Oh yes, I see why these numbers are quite interesting.
1, 2. So the function. Do we know where the turning points are? We don't know that.
I don't know that yet.
Probably looks something like this. Let's say it looks something like that. We don't care about that because we only care about the function on this interval 0 to 2. So let's say that. and then there's some c, and you know what to do.
Yes, yes. So the important thing is, if you look closely at this function, so, and we'll see this when we actually just go algebraically through it. So let's see what we have so far. Right. So we have, so f of 0, that's easy to calculate because if you put into zeros into this, both terms, almost all the terms vanish and you just get 5. And what's interesting is if you look at f of 2, well, that's going to be 2 cubed minus 2 times 2 squared plus 5. So it is very interesting because that is also a 5. So that's, you can see that in this picture here. The function starts at 5, does something, ends up back at 5. So the slope here is nice, represented by, so I can draw this. This line has the slope 0. So the average slope over this interval is 0. Right. Alright, so we have that. Well, we also what we're looking for is a point where f prime of c is equal to 5 minus 5. Now the interval is actually of length 2, but that's not important because you have a 0 on top, so it's going to be 0 slope. And in terms of this function, that derivative is going to be no, sorry, not x, c. Get that right, yes, bring in 2, yes. C, yes. So if you take the derivative, you will get this quadratic, and I've plugged in c. So I'm looking for points where this is equal to 0. So these are actually, so the question actually comes look for the turning points, right? So now we're going to find the turning points anyway. So factoring, you have c outside of 3c minus 4 equals 0. So I'm going to be very careful with my language here. So possible c are either 0 or, well, either making this 0 or this 0, which is 4 over 3. So far we've actually found that there are 2 turning points to this cubic. One is actually over here at 5, and one of them is over here at 4/3, so 1.33333, so on. So around about here. That's where that turning point is. Now, the reason I'm being quite careful here is because while there are 2 things that make this vanish, if you go back and look at the mean value theorem, it promised me one in the open interval. It says it won't be on the endpoints. You'll definitely find one in the interior, somewhere inside this interval. So the one that is promised to me is actually this 4 over 3. This one isn't the one that the theorem is promising. It says, I promise you there'll be one, and it'll also be between 0 and 2. So, so how will I state that? And
just 4 over 3 is in the interval.
Yeah.
As promised.
Yeah. And since I might say that since 4 over 3 is the one which is in 0, 2, it is the promised point.
It's the point that the prophecy foretold.
Yes, the mean value prophecy.
We should call it the mean value prophecy.
Yes, I mean that's what theorems are. They are promises to you that as long as you have the right setup. I mean, I didn't verify the setup here because it's quite easy to see it does work. But if you have the right setup, it says, I promise you, you'll have this result.
Yeah, this one has more of the hallmarks of a prophecy though, because it doesn't actually tell you anything useful about how to get there. It's just like, it's going to happen.
Yes, that's true.
We had to rely on some other kind of machinery to actually figure out where that C was. And I really like the picture. Whenever I see a mean value theorem that involves the picture, and really the whole theorem can be stated almost with the picture as well, because it just tells you that this one. Thank you. that there is some c such that the slope of the function at that point is equal to the slope between the endpoints. And the whole theorem is just summed up neatly in the picture. So I love the picture. I think we should also change the question to give a pictorial representation of the mean value theorem, because it's just as informative. And if you do get asked a mean value theorem question, draw a picture, because it'll help.
Yeah,
I think it'll help.
And definitely, it shows. Also, I like seeing that students really do understand what these things are talking about. So
yeah, I mean, it's easy enough to just memorize verbatim what the mean value theorem says, but that's not going to really help you, I think, to solve questions. What helps you to solve questions is an understanding of what's going on.
Right.
Cool. Next one.
Sure.
I'll flip the question over.
Cool.
Thank you. Okay, this one looks easy. Not so easy though. Find this limit. So I'm going to let f of x be equal to x sine and g of x equal to 1 minus cos x. Then the question asks me to find I'm going to call this L0 of fx over gx. This is my question. Now, you may have noticed that this is of an indeterminate form, so this is precisely the kind of place where you start thinking about applying the Hopital's rule. But the Hopital's rule is really, I think, poorly executed generally, because people tend to mix up what you need to invoke it and what it promises you. You don't know necessarily that this is equal to, you don't know necessarily that the Hopital's rule is going to tell you anything interesting. It only promises you the value of the limit when that limit of the derivative, ratio of the derivatives, actually exists. So well, maybe I'll say, since it's indeterminate, and by that I mean, well, what happens when x goes to 0? This goes to 0 and this goes to 0. So 0 over 0. This is one of the two indeterminate forms. When you've got something which is like 0 over 0, and I say 0, I say with kind of quotation marks, because that just doesn't make any kind of mathematical sense. It's not a number. And also infinity over infinity, whatever that means, is also the other indeterminate form. Since this is indeterminate, then L0 will be equal to L1, which is lim x goes to infinity of f prime of x over g prime x when L1 exists. So we don't know that this is actually going to be equal yet. This is only guaranteed to work when L1 exists. So there's a condition. We can't just straight up say, then this happens. This happens provided L1 exists. So it's a bit like Inception at this stage. So I'm going to switch colors. To solve this question, we actually need to solve another limit question, a limit question inside the limit question. Does L1 exist? Let's find out. So L1 is lim of, well, the derivative is, what's that? X cos Sine goes to cos, right? Yeah. Over, and 1 minus cos goes to negative sine, so this is sine x. This thing, and when x goes to 0, this is 0 over 0, again, of indeterminate form. Then L1 is equal to L2 is lim. Again, I'm going to apply the Hospital's rule, but one step deeper this time. When that should be a 0. When x approaches 0 of f double prime of x over g double prime of x, then this when L2 exists. So how do we know if L2 exists? Well, we have to go deeper. And L1 exists, we have to go deeper to L2. Now L2 is lim x approaches 0. The derivative of this is, let's see, x cos goes to negative sine, x cos plus cos, x plus cos x, all divided by sine goes to cos. And this one's okay. This is just 0 plus 1, so it's 2 over 1, which is 2. Great. We've finished out. We don't need to go any deeper now. We know what L2 is. L2 is 2, which means L1 exists and is 2, which means L0 exists and is 2. So we'll go back to the original blue, hence L2 is equal to L1 is equal to L0 is equal to 2. Bye. By the Hospital's rule, which I really used 1, 2 times. Twice. Josh.
Yeah. So yeah, this is quite important subtlety about L'Hopital's rule. I sometimes think we should have a question in a test which just is explain why L'Hopital's rule fails. And it's because sometimes you might have something where the limit doesn't exist, but that doesn't actually stop the limit from existing previously. So luckily at the end of, well, thankfully at the end of this chain of dreams, there was actually a limit that existed. So yeah, then the information floods back up the chain. If Daniel had gotten no limit here, he just has to find a new technique for attacking this limit.
Yeah, it doesn't actually say anything about the original limit.
There's different ways you could try and answer this. This is, I think, a nice way. Make it very clear that you understand that attempting this may end in no information whatsoever. That does happen in mathematics, where you put a lot of effort in to try and find something, and you just find that you found nothing.
Yeah, it reminds me of my PhD.
Right, yes. But thankfully, you did get it in the end. So it reminds me of the start of my PhD, I guess. Let's not say I found nothing at the end.
It's a common story.
All right, but yeah, this is very nice, and it's very clear that Daniel's being very clear, explaining that yes, this may not actually give me anything in the end, but in this case it does. Right.
Next one.
So next one. The other board. All right, I'll flip it over. So Okay, so we want to take this cubic and work out how many solutions there are and state. It says here, give reasons for your answer, stating any theorems, naming any theorems that you're actually using. And they give us a very big hint. They say that you should be looking for the number of stationary points. So let's do that. Let's first look for the stationary points of the polynomial given there. Now, this polynomial doesn't have a name, so I'm just going to give it a name. Let's let f of x, f be the function which behaves like x cubed 6x squared plus 1. Alright. For which, well, the derivative, let's say d of dx, is just 3x squared minus 12x. And that's very nice, because that factors very nicely. There's actually a common factor of 3x and x minus 4. So from this we can immediately see what the roots, what the stationary points of this will be. It'll be when either x vanishes or x minus 4 vanishes. So x is 0 or x is 4. Right, so there are two stationary points. Now, if I knew what the value at those stationary points were, I'd have a very good idea of what this looked like. So what do we have? And you have that f of 0, well that's easy to calculate, it's 1. And f of 4, it's not as easy. It is 4 cubed minus 6 times, well, let's say 4 squared plus 1. Alright, 4 cubed is 2 to the 6 is 64. This is, so this is a 16, 32, 96. That's actually minus 3 times 32, plus 1. And alright, let's make this 65 minus 96. And to be honest, I'm not very good with negative numbers. I'm going to make that because, well, make it into something which I know will be positive, because I can do it a bit easier in my head. So this is up by 31. So it's minus 31. Alright, so I have a very good idea of what this function looks like. It's a stationary point at 1 and a stationary point at minus 31. Alright. So let's see. I'm going to make a small table just to make sure I understand what's going on. We do have so that going from minus infinity up to 0, 0, 2, 4, from 4 to infinity. This is just my some intervals, and I want to look at the derivative over that. Well, you can see that it actually is a negative derivative. So for large negative numbers, these are both. Sorry, if it's a positive derivative. Wait, yeah, positive derivatives there. It's a negative derivative in this range where this is positive and that is negative, and then when they're back both positive, you get a positive derivative there. So it's always increasing on this interval, always decreasing on this interval, and always increasing on this interval. Now a picture here is quite helpful to make sure we know what's going on. It'll help me motivate my final statements. Right. So we know where the stationary points are. I do need the function values just to make sure I'm doing this right. so we have, go through 1 here, let's say that's minus 31 there, cubic does this. That was 4. This diagram is widely not to scale, but that doesn't really matter. Alright, so we can see there's a change in sign here. So well, there is a change in sign from here to here, where the function is increasing. Now I always wonder about this one. For cubics, you know that for very large negative numbers, they are negative. So I don't really want to go through and find a number for which gives me a negative number. I know one of them will exist. So I feel it's justified to say
-1.
Right, so well, okay, so maybe I'll be a bit more explicit. Right. So, okay. The voice in my head suggests f of -1.
-6.
Okay, and that gives me -6. I just can quickly check that. So that gives me a -1. That's a -6 plus 1. So yeah, you use the middle term is the only thing that survives that. -6. So it does change sign here. So since there is a change of sign and f is continuous, there is at least one root, so there is a root by the intermediate value theorem. I'm being a little bit lazy just calling it the IVT. Now what's important is there's actually only one root, and that's due to the fact that over this range it is strictly increasing. So there is a root by the IVT. I'll store these ones in memory, come back to it. And since, well, I might say it as since the derivative is positive in this range, this region, it is the only root. So it's actually what you call monotonically increasing. It's strictly increasing on, in this case, -1 to 0. So yeah, so that's important. There is actually only one root in that range. Now we can see that there's going to be another root between 0 and 4 somewhere, because we go from a positive number to a negative number. So again, since f, in this case f of 0 is positive, f of 4 is negative, there is a now look, got to put that sign up.
Another half hour. It's not a problem. So I think I just have to do a rough cut of one of mine, which we'll polish up. I can leave it till tomorrow.
Right, so there is a change of sign in that range. We're actually live streaming, so.
Oh, sorry.
Right, so yeah, there is a change in signs in that range, and you can actually see that the derivative is negative. It's always going down. There is again a single root. I won't repeat the reasons. The reasons were given here by IVT and the monotonic. This is the same reasons, just one of the derivatives. The derivative is a different sign. And of course f of 4 we know is negative. And it shouldn't be too hard to find a point. The function does start increasing after that. So I could maybe just pick a large positive number an easy one to deal with would be, say, 10. So if I was going to do it explicitly, f of 10, for example, is 1,000 minus 600 plus 1, so that's 401, which is definitely positive. So again, since there is a change of sign, and f, now the derivative is positive over 4 to, in this case, 10, there is again a single root here. Now the fact that it's positive, always increasing, there's not going to be any more roots past 10, and there's not going to be any more roots beyond -1 in the negative direction. Hence there are
Cool.
It's not the best solution, I must admit, but it does do its job. And I think there is still something missing from the argument about the outside the range. But I never wrote down the strict there.
You could say that it's cubic and has no more roots than those 3.
That's true, yes. So yeah, cubics are nice. They will have at most 3 roots.
3 real roots.
Real roots. They always have. Well, they might have.
You could say that. You could also say that it's a real coefficient polynomial, and therefore has either 1 or 3 real roots.
Yeah, so that would be a nice way of doing it. This is bringing the algebra knowledge we've been acquiring in the other half of the course.
Yeah, I mean, this is the intention. I'm pretty sure this is what they want you to do.
Yeah, I think really they want you to be talking about the intermediate value theorem. That is the important theorem here, and you do need to make a mention of this strictly increasing or strictly decreasing. So
yeah. Well, theoretically, you could get away with. I mean, this is the answer they want, and my advice is give them the answer they want. Theoretically, though, I wonder if we could do it without mentioning that, because if you know there's at least 1 here, at least 1 here, and at least 1 here, and there's at most 3, then there's exactly 1 here, exactly 1 here, exactly 1 here.
okay,
So you could do it. Don't do it that way. Mention monotonic. Don't do it that way. Mention monotonic.
Yeah, I see what you mean, because the intermediate value theorem will give me 3 different possible roots.
Yeah.
And actually.
Yeah.
But no, I think I would want you to realize that the derivative does play an important role for sort of pinning it down to 1.
I'm just being cheeky here. Let's move on. Oh, I'll just swap it over. Okay, so I'll show you 2 methods on how to differentiate this function. The first method is one that's perhaps the most familiar with you. Is to recall so we'll call this one the table method. And this is perhaps the one that would be most familiar to you, because you might remember from your standard table of integrals, or even if you're doing a final exam and you have a table of standard integrals in front of you, that, let's see, the integral 1 on you might remember that. and you can convert this. You can essentially use this relation to get at your answer. It's not my favourite way of doing it, but it'll work. It'll work. We just need to figure out what to do here. So in this case, we'll let we want to let a be equal to 1 and z be equal to 4x plus 1. Then this becomes 1 on dz. And then we can differentiate this with respect to z to deal with this. So dz. No, wait, we want to differentiate this with respect to x, sorry. X. Well, there's something going on here, because the only sensible thing to do to this would be to differentiate with respect to z, but I want to differentiate it with respect to x. So I want to use a d dx here, but I also want to use a d dz over here. So I will, but I need to balance out the d dx. With that. Oh, sorry, that's squared. D. And I can just drop off the c now because that got differentiated away to 0. Dz dx, that's just 4, and this is just well, that cancels with that stuff cancels away, and you just get that thing. So this becomes d dz dz dx is just 4. This becomes 4 on 1 plus 4x plus 1 all squared is equal to the derivative I'm after. That's one way of doing it. That may be the most familiar way to you from school as well. Let me show you a different way. This is where you let, what am I trying to integrate here? So let y equal tan inverse of 4x plus 1. Then you can rephrase this whole thing as tan of y is equal to 4x plus 1. And then I can differentiate this whole thing with respect to x. Now remember, what I'm after here is dy dx. So this is d dx of tan y is equal to 4. This thing, I can't differentiate this with respect to x. I can differentiate it with respect to y, so I will. This one can be equal to dy dx times d dy tan y. And this is just sec squared. So I pick up a dy dx times sec squared, which I'll bring on the bottom here. Y, sec squared of y. And remember, sec squared of y is 1 plus tan squared of y. And tan squared of y, well, that's just 4x plus 1 all squared. Which is the same as that. So you can go either path. This is by far my favorite path because it doesn't need you to remember anything. But both roads will lead you to Rome. Josh.
must admit, I've never actually seen it written this way with the integral. It is correct. But,
It might be a bit weird.
What was making me feel a bit uncomfortable at first was seeing this dz and this x together. Because
Fair enough.
It is actually correct if you work through the details.
This is not the path I usually take.
This is. I don't like them. I much prefer this one.
Would you prefer with z's here? Would that be better?
Well, I guess what I would maybe change is you could change the dz using this relation here.
Yeah, I suppose I could do that.
It is a sort
Yeah,
of
that would work. That's nicer, actually.
But even then, well...
Yeah, I like that. Because then it's just 4x. Yeah, let's do that. Because then that simplifies this whole process. That just becomes dx, and that's a 4.
Yeah. So now it is just... Yeah, now I
lose a whole line. Brilliant. There we go.
Yeah.
Check that out.
That is, and that's fundamental theorem of calculus, the first one. Actually, I quite like this. The only thing I guess might trip me up is I don't always remember the relationship between sec squared and tan squared, but I remember the definition for sec, or I remember the definition for tan, so it is easy for me just to...
I always remember cos squared x plus sine squared x is equal to 1, and then just work it out from there.
Yeah, so you divide that by cos squared x. It immediately gives you the result. So yeah, this is probably a fact you can easily remember.
Yeah,
so
you need at least one fact. So I'd take that one.
Yep. And yeah, I like this. I like this second method. It feels nice to me. This is also good, but
it requires you to remember something, and I don't like remembering things, not in general.
Right.
Cool. You're up.
Next one is it was a critical point question.
Second last question.
Yes.
Hooray.
So we're given this function. There was a typo in my original slide. Hopefully I fixed it. It should be to the 2/3 power. Is that correct?
It's the 2/3, yeah.
Good. All right. So we have this function, which is actually a nice continuous function. And we're looking at the interval 0, 2, and it says to giving reasons, find all the critical points. Now, this function is quite nice because it has all 3 types of critical points in it. So let's try and maybe just go through the types one by one and look for them. So, oops. So the critical points are, well, the endpoints of the interval, i.e., well, in this case, the endpoints of the interval are 0 and 2. The other type you can run into are the stationary points. i.e., well, we're going to have that f prime is equal to 0, the f prime of x, which is going to be, bring them 2/3, I get 2/3 x minus 1 to the minus 1/3, and that's where that is equal to 0. Extra points are that. So this only has one critical point. There's only one way to make this equal to 0, which is when x equals 1. So only 1. Maybe I should say x equals 1, that would be a bit clearer. So we have those 2 points, these points, and there's one more type of critical point that we can find. The points where f is not differentiable. Now, in this case, I've already calculated the derivative here, so I can see that most points this function is nice and differentiable. For most numbers, so I plug it in, it gives me did I make a mistake?
I think your stationary point.
This is this is on, because when I put an x equals 1 there, that becomes 0 to the minus 1/3, which is not correct. So I guess there are no station. I think is there a way to make that function equal to 0? Because no, I think there are no stationary points for this function. So I've actually made a mistake. Yeah, sorry, I was too focused on thinking about making this thing inside 0, not paying attention to the power. So
yeah, no stationary points.
Yep, that's correct. Alright, so the stationary points are when this is equal to 0, which never occurs. Okay. So actually, we only have 2 types of critical points. This one never does actually happen. And the point where it's not differentiable, actually, this is the one where this breaks down. When this thing inside here tends to 0, the derivative is not defined. So this is x equals 1. And that is in the region given the 0 to 2. Alright, so there's actually 3 critical points, 0, 2, and 1. And 1 is in that range. Okay, so next thing we want to do is use this information. Now it doesn't say use this information, but really that's what the intention. Find the absolute maximum and the absolute minimum of this function. Right. So I might be able to squeeze that in here. Now, important fact, since f is continuous, on the interval 0, 2, the min-max theorem says so it says that they actually do occur, and actually slightly stronger statement, and moreover occur at critical points. Alright, so there are only 3 critical points. All we need to do is look at what they're doing, and they will give us the maximum value and the minimum value once we sort of sort through them. Okay. Alright, let's just get some information. So the first critical point we had was f of 0. So if you put in f of 0, you get minus 1 to the 2/3, which you can think of, I might rewrite this as minus 1 squared to the 1/3 power. It might be a bit high, but that is 1 to the 1/3, which is 1. The next critical point along was at 1. This is the non-differentiable point. You get f of 1 is 0 to to the 2/3, and 0 to a positive power is just 0. And f of 2 is 1 to the 2/3, which is again just 1. So we have these three pieces of information, and we know that these must contain the max, absolute max and the absolute min, so I can see that the absolute min must be the 0. And yeah, and the absolute max must be the 1, so hence is 1, and the absolute min value is, in this case, 0. Sure, yeah. You might have been able to spot that one from more just looking at the function, that clearly 0 is the smallest value, but this is sort of a nice way of using the critical points to find them. Right, any comments?
I like it. It's a good question. I like the whole theorem actually, because it actually tells you where to look, as opposed to the mean value prophecy, which just promised you is somewhere. This one actually says, oh yeah, just look at the critical points, you'll find it. It'll be one of them.
Yeah. So it's a nice small list to check.
Yeah.
Right. So final question.
That's me.
Yep.
I'll do that. So this is a curve sketching question. Curve sketching is new to this class test, and because there's no samples of it in the class test that you've been given, I've put a sample on Moodle. So if you look in the announcement section on Moodle, you'll see a whole test which is exclusively curve sketching. It'll give you a feeling for what kind of stuff that you could be asked. So this question, sketch the graph over some interval of a function which is defined in this way. Here's my sketch. Okay, the first thing it gives me is the function x minus x squared in the interval 0 to 1. So let me just put out what my 0 to 1 is here. 0, that's 1. And it says the function is x minus x squared. So that's going to look something like an unhappy parabola. Like that. Which peaks 1/2. Good. And then the function tells me that it's odd. It's an odd function. That's what that second line's telling me. So that tells me, well, I know what odd functions look like. They have this kind of point symmetry with the origin, so it must look like at least this. And then the function tells me, and then the final statement is telling me that f of x plus 2, so this one is equal to f of x. So this function just repeats itself every 2. So it ends up looking like some kind of, not exactly a sine function here, because this is a segment of a parabola and it's mirrored down here. But it's got that kind of periodicity like a sine function. Sorry. And that's all we have. Josh, would you add anything to that?
No. I mean, the picture, I mean, it gives you all the rules about what's going on with this function, and you need to understand how those rules will affect. So this is nice. Just 0, 1 is what we start with. We get a little bit more information, and then that last period condition gives us everything else. So I can't imagine you really need to write anything down for this question. It is a sketch. You might, maybe if you wanted, you could actually write down in words what Daniel was saying.
Yeah.
Say what these conditions really do mean, how we interpret them.
Yeah, maybe I'll do that.
Yeah.
So y equals f of x. Sorry. X squared minus x is. So that's in this section, and then f of x, negative x. I shouldn't say is. It means. Means this is an odd function, and finally f of x plus 2 equals f of x. It's periodic with period 2. So just saying in words what the 3 conditions you were given are.
Yeah. It's a very curious function, actually. I was just checking in my head. It does actually meet up with the tangent being the same.
Oh, nice. How nice.
It does, because this is, you check, this is slope 1. So when I flip it over, still slope 1. I'd be curious to know what the derivative was, but I wouldn't spend that
No.
I wouldn't do it in the
Don't
class
do
test.
Yeah, sketching is enough. Yeah, just being aware of what these things are and what they mean in terms of geometry.
Yes. Just I think if you do it, it does turn out to be continuous. It is differentiable everywhere.
What a nice function.
Yes. All right. So we should stop there. We've actually going for 2 hours.
Damn. Okay. Cool. Well, thanks for joining us. Is there anything we need to say to people about the test? It's 45 minutes long. Go to your TU1, which just like in your last test.
Yeah.
What else do we need to say to people?
Good luck.
Good luck. Yeah. Cool. Okay.